Great. So totally a grade 11 review thing, but we should really talk about these different kinds of forces just as quick as possible. And we're in the notebook, but when we talk about air resistance, what's the D word that people think of? Yeah? Drag, yeah. So oftentimes we'll talk about the drag force. And of course, that's just the force that opposes your motion as you try to move through the air. I mean, it could actually be a direct wind blowing force, like a balloon being blown in the wind or something like that. So we might want to distinguish between the two. An applied force. Now, applied force is really kind of an umbrella term, and oftentimes, just because of the teacher that I had when I was young, I used subscript APP for applied. You may see capital A for applied. Fair enough, okay? But it really is just that umbrella idea that something is pushing or pulling on an object, and it's an external force. And then we have the buoyancy force. What's a scenario where buoyancy would be an issue? Yeah. Well, yeah, anything involving water. So a boat, currently I have a big yellow dinosaur floating in my pool. It is experiencing a buoyancy force. If it deflates, I don't expect it to sink because it's mostly made out of plastic anyway. It would still have a buoyancy force, but it wouldn't support a human anymore. The buoyancy force would have been reduced at that point, right? So it's full of air. So good illustration that people talk about, just a ball in water. And if you're somebody who fishes, then you might have encountered what they often call a bobber, and a bobber bobs up and down. But that bobber would experience a buoyancy force. And sometimes people will write it FB and sometimes FBOUY for buoy. And then we've got FG for gravity. And what would the relationship be for the FG and the F buoy if it's floating? How would they relate to each other? Like what would the one value be compared to the other? Yeah. Oh, the buoyancy force and the gravity force? No, not one greater than the other? No. Yeah, they'd have to be equal to each other. They'd have to be balanced. It would be an equilibrium if it's just floating, right? If Fg was greater than F buoy, it would sink. And I suspect that you've seen things sink. Like, I mean, I think about things that I see sink. I'll go back to that swimming pool when the kids throw the colored rings that people try to race to see who can get them off the bottom. There's definitely a buoyancy force on those rings. They don't sink quite like a rock. They sort of flutter down, but the buoyancy force isn't as much as the gravitational force. So they're going to sink, right? And then even in the air, there's actually a buoyancy force that drives balloons upwards. Would you believe that? The buoyancy force, it's not water in this case, it's the atmosphere, but that balloon's going to go up, 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 up. Now, there will be a point where that balloon gets to a point where its buoyancy force is no longer strong enough to be bigger than gravity. It actually gets to a maximum altitude. It gets to a maximum altitude because the atmosphere isn't uniform. You guys know that the atmosphere at lower altitudes is more dense than the atmosphere at higher altitudes. And so it will actually get up there. Density is going to be an issue. There's also temperature that's an issue. And so, sort of battling that, the balloon's going to contract. But at some point between the contraction of the balloon, which is going to be forcing the air inside to be more dense, and the atmosphere itself becoming less dense, it's going to get to the point where the buoyancy and the gravitational force equate. And so it's going to have like a hover altitude. So balloons actually have a hover altitude. It's just that there's no top of the water. It's a little bit more nebulous. Like it's not a distinct exact height that it's going to hover at. But I would suspect, and you can do your own research, there's probably a range of heights that a balloon would hover at, based on average latex elasticity or something like that, Anyway, other things that we talk about types of friction. We've got static friction and kinetic friction. And according to the notes here, it says that static friction is that kind of friction that keeps something from moving in the first place. And kinetic friction is that friction that occurs when something slides across another something. And oftentimes, if I'm doing this as a cartoon illustration, I think about there being a rough floor and there being an object that has a rough surface. And when we're talking about static friction, we're typically talking about the roughness of the one surface and the roughness of the other surface being interlocked with one another. And you can push, 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 and as long as you don't disengage the teeth, the interlocking teeth, now they might be like physical traction type teeth, or it might be like surface on surface electron cohesion, but whatever it is that's causing that friction, it's locked. Static friction is when the lock slips and they start to skid across each other. And it makes sense, and here I'll like hold my fingers up here. I think of my fingertips as being locked together as I try to move my hand on the right upwards and my hand on the left downwards. And I can push, 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 push. As long as those fingers are engaged, it's static. But as soon as they slip, the teeth like jitter across each other, the ridges jitter across each other, that's kinetic. Okay? And I think we can almost like feel that. Like when you imagine like dragging something across a carpet or Velcro on Velcro, like that. I mean, that would make shivers go up my spine, but it's that kind of a feeling. And what we say as a result is we talk about this being the stuck scenario, and this being, I won't say moving, I'm going to say sliding, because I want to make sure that it's really, well, not sliding. I want to make sure that it's really clear that we're talking about surfaces sliding across each other, not just moving, because I don't ever want to think that a rolling wheel is sliding unless it really is sliding, right? Like icy conditions or whatever. And like, got to make distinctions. The other thing that we notice as a pattern is, and we could experiment with this if we want to, but as a pattern, what people have noticed over and over again is that Fs is greater than Fk. That disengaging force is bigger than the skidding force, in other words, right? And in terms of a formula, I haven't done this for the other ones, but as a formula, we say that in general, I'm just going to say force subscript F for friction, because I could say Fs or Fk, but friction force is equal to the coefficient of friction. And again, I'll just use F as a placeholder, coefficient of friction, because I would use mu S or mu K, depending on if it was static or kinetic. And then, what's my last F word? Yep. Normal. Yeah, the normal force. And so we talk about an object that's sitting on a surface or pressed up against the surface experiencing a normal force. And that's actually the next force in my list. So if I'm talking about a horizontal surface, I might talk about a table, talk about an object on a table, and of course, yeah, there'd be a force due to gravity, but I don't even think I want to draw that in right now. I just want to think about the fact that there would be a normal force acting up. And yeah, of course, there'd be a force due to gravity acting down on it. I'm going to do this in a different color because I want to make sure that it's really clear. And maybe I should have done it back up here with buoyancy, because although we're not talking about it right now, there's going to be somebody at some point that thinks, oh, those are action-reaction forces. Oh, by golly, no. If this thing floats at a constant height, they happen to be equal forces and opposite in magnitude. This normal force and this force due to gravity happen to be equal in magnitude and opposite in direction. They are not action-reaction forces. Okay, so let's just make sure that that's something that everybody knows I'm not saying. Okay, we'll come back and talk about action-reaction forces are, but those two are not an action-reaction force pair. They absolutely are not, okay? And even if we wanted to drive that home a little bit, we could talk about, well, what happens when there's an object on an incline? And in this course, we're going to talk more about objects that are on inclines. And the definition of a normal force is that contact force that lies perpendicular to the surface of contact. And so if we've got a surface of contact that goes on an angle, force due to gravity is still down. Nothing changes there, but the normal force is going to go off in this direction, such that it's at right angles to the surface upon which it sits. That's the normal force, okay? And that fits with the written definition that's there, but I just want to make sure that we recognize that couldn't possibly be confused as an action-reaction force pair, right? They're not in opposite directions. And what we're going to find later is that they're not even equal magnitudes. And we'll deal with that later. That's not something I want to go down the rabbit hole of right now, but they're for sure is not action-reaction force pairs. And then the spring force, now sometimes we use Fs for spring force. Sometimes we use Fe for elastic force. I mean, obviously I've already used Fs for something, static friction force, and Fe could, although I haven't used it yet, be used for electrostatic force. And so there's not like a right one, but what you'll find is that people just kind of situationally decide on them. Like I often just like Fs because I like springs, but if there was friction, I would have to switch over to Fe if there was like a spring and friction problem. So be situationally appropriate. People will understand what you're talking about. If you have spring force, elastic force, and electrostatic force, God help us all, right? Like, I mean, that's going to be a tricky question, and we're going to have to maybe have a slightly longer subscript. It'll be ugly, okay? And it won't be that big a deal. All right, so we have ourselves an object, and sometime we talk about a spring, and if this was my spring with nothing attached to it, I could say, okay, well, this one is that spring with something hanging off of it. And maybe I take this same spring and I mount it on a tabletop, but I stack another object on top of it. That same spring has now become squished. So we talk about different spring scenarios. People even engineer different spring types. So we might talk about an extension spring, and we might talk about a compression spring. And some springs can do both. But if you have a spring that's been designed with no gaps between the coils, that's not a compression spring. And I think about like I used to have a trampoline as a kid. And the trampoline springs, if you ever look at trampoline springs, the coils are butted right up against each other, right? You can't compress those springs anymore. They stretch. They're extension springs. But at the same time, when I look inside of my pencil, I guess if it's not an electric pencil, a mechanical pencil, or like a Bic pen or something like that, if you tear it apart and you get the spring, and I think like everybody's played with that little doingy spring, there's gaps between the coils, that's definitely a compression spring. And whatever the clicky mechanism is within your clicky pen, that spring is compressing to hold that ink cartridge in place, right? So we know that we've dealt with compression springs. Your bed springs are compression springs. Anyway, we don't have a different letter that we use for extension springs or compression springs, but what we do think about is with the free body diagrams. Now this is an illustration, it's not a true free body diagram, but if these masses were the same, they would both have FGs going downwards. But with the extension spring, if I deform the spring by extending it, then its tendency, and sometimes people like anthropomorphize their springs, they'll be like, oh, the spring tries to restore itself. But it does, it's restorative, right? It's trying to restore itself to its original undeformed length, like illustrated here on the left. And so if the FG stretches the spring, then the FS tries to return it to its original length. And if the FG is compressing the spring, then the FS, again, is trying to restore the spring to its original length, but that means pushing up on the object. It's always working counter to what you're trying to do. Springs, whether you're stretching them, and they're trying to get back to where they're going, or if you're compressing them, they're trying to get back to where they were going in the first place, or what they were tending to be in the first place lengthwise. Tension. Well, maybe I should make a little note of that. Always opposes or resists the distortion force. And then tension. We actually have had a few different scenarios in previous work with tension. One scenario we had with tension was objects, for example, that were tied to a rope so that one object dangled over a pulley and the other object sat on a horizontal surface. Another scenario that we had was, again, with pulleys, but with one object dangling on one side and the other object dangling on the other side, and the force due to gravity acting on both of those objects, working to somehow cause tension inside of that rope. The force due to gravity on this one, and not the force due to gravity so much on the surface one, but perhaps friction being a contributor to how much tension there is in this rope. And I'm not going to go down the rabbit hole of how we would calculate that tension, but the idea is that in both of those situations, force is transmitted through the rope. And an even simpler scenario would be like if I have, just with this idea of two objects carrying forward, if I had a person and this person was pulling with a rope as they dragged two boxes, there would be tension in the rope between them and the first box, but there would also be tension between the two boxes if the boxes were tied together. And this sort of like conjures up the idea of how the tension in coupling units between trains might even be an issue, right? So I mean, like, lots of different situations we could talk about tension, but always the transmission of force through a rope. Now, as I look at this, if this was object 1 and this was object 2, and I was like forcing myself to think about the tension between the boxes, as opposed to the tension between the human and the first box, that actually is an example of an action-reaction force. Because it turns out that there's a force where object 1 acts on object 2 through the rope, but there's also a force where object 2 pulls back on object 1 through the rope. And that truly is an action-reaction force. And if I was going to force this issue and say, hey, I'd like to think about how those two forces are acting, what direction they're acting on, if this was object 2 and this was object 1, force of 1 acting on 2 would be this one. Force of 2 acting back on 1 would be this one. And what I want to highlight with tension is that, yes, it's transmitted through a rope, but when I apply the idea of tension to a free body diagram, we have to make use of Newton's third law. Okay, so really, anytime I deal with tension, Newton's third law is actually kind of just playing in the background, and we kind of have to recognize that. Lift force. So with lift force, here, I'll just do a quick illustration, and it won't even be a very good one, but imagine if you have like some sort of a single pilot jet. Okay, I won't even put the other wing on there, but side view, single pilot jet. We know that there's going to be, we've already mentioned the idea of drag. So this isn't truly a free body diagram, it's more of an illustration with forces attached to it. But we would have a drag force acting back on it. We discussed that. That was our first force that we talked about. We'd have Fg acting down on it. We could call the forward force the applied force. A lot of times, specifically with jets or any kind of like propelled vehicle, people will call it the thrust force. So, watch out for that. If you see the word thrust, it's just, a dressed up propelled vehicle name for an applied force, okay? But then the lift force is going to be this way. Now that lift force, when we're thinking about it in this way, isn't buoyancy. It's actually because of something called Bernoulli's principle. And if you want to go down, again, the rabbit hole of how Bernoulli's principle works, it's really a fluid dynamics thing, where when the airflow above and below an object like a wing is a different speed, there's a difference in pressure. And that difference in pressure causes lift. And that's, again, not quite a rabbit hole I want to go down to, but I'll say it again, Bernoulli's principle, if you're into aeronautics, that's what drives lift force, okay? And you can find a YouTube video about that one. I'm 100% sure about it. And if it's confusing, come back and talk with me about it, okay? But that's actually like kind of an interesting thing. My daughter's been asking questions about that recently. So we've got free body diagrams. If I was going to take this illustration and turn it into a free body diagram, and this is like a good candidate for a free body diagram, I don't draw a jet. I draw just a plain old, something like a geometric shape. Circles and squares and rectangles are the preferred shapes, it seems. And we talk about the forces acting on the center of mass of that free body, that object that we're modeling. So I've got Fg going down, I got F lift going up, I've got F drag going back, and I've got F thrust. Now, when I draw these diagrams, I try to be kind of scale-ish about it. I'm trying to make the scale be, kind of roughly always one bigger than the other or whatever. Now, if you want to be really strict about it, you can set like an actual scale. You can use like a ruler and say like 1 Newton equals 1 millimeter or something like that. You can definitely do that. But I'm going to be a little bit more free and easy about it. As I look at this, one thing I might want to do is set up, or not one thing I might want to do, is one thing I definitely want to do is say that I have a reference frame. So forward, up, down, back. I want to define which directions are positive. I'm going to call up positive and forward positive, and back and down negative. You don't always have to do that. It might be useful to have down be positive. If, for example, like this was a jet that was dropping off food relief or something like that, and you're dropping food relief off to, somewhere where there was a forest fire or something like that, it might make sense for down to be positive. So down doesn't always have to be negative. Just make sure that that's very clear. But We need a reference frame. Need. That's essential. But then as I look at this particular free body diagram and the way that I've drawn it, assuming that I had some sort of rough scale, what can you tell me about the motion of this thing? Because that's something we could pick off from a rough scale diagram of an FBD. And that's the short form for free body diagram, FBD. Somebody help me out. What would the motion of this jet look like? Yeah.
It's moving forward because the thrust force is greater than the drag force.
It is moving forward. Now the thing is, it could be moving forward even if they were the same length. So something special about it moving forward. Yeah.
It's accelerating forward.
Yeah, look at that. See, if the thrust force is bigger than the drag force, then the net force in the x direction is going to be to the right. So it's going to, if it has a net force, I'm getting ahead of myself here because it's Newton's second law, but if there is a non-zero net force, you're going to get acceleration. Okay, so that's definitely accelerating. What about in the y direction? What could I pick off about the motion in the y direction? Yeah?
It's like not going up or down.
Yeah, well, so that could be an option. If the forces are balanced out, then they would add to 0 in the y direction, so F net would be 0 in the y direction. And so one assumption could be that it's not going up or down, it's maintaining a constant height. That could be a thing. This is a hard one to sort of like remember too. If those two forces are equal to each other and the net force in the y direction is 0, it might be that it is moving. It might be moving at a constant velocity because the acceleration is 0. You could be just drifting up at a constant velocity or drifting down at a constant velocity. It could be that you're drifting up or down at a constant velocity, or you could be flying at level altitude. Okay, so those could be two different conclusions you could draw out of the same free body diagram. And I get, because I would make the same assumption as you, that it was flying at a constant altitude. But it is also possible that 0 acceleration doesn't just mean that it's sitting at the same height, that it's just moving at a constant non-zero speed up or down. So like that's kind of a tricky thing. So I just wanted to, I knew you were going to say that. Everybody says that. So I want to make sure that we didn't get stuck on that one. Let's take a look at the next page. And I am going to go a little bit faster through this page, I think. We're talking fundamental forces here. And I know it sounds like that should take longer, but we are kind of going to unpack these ones a little bit more slowly over the course of the semester. Gravitational force, oftentimes we write it as F little g when we're talking about the force due to gravity near the Earth's surface. And so people will write it like F little g mass times acceleration sub g, or they'll write it as F little g equals mass times just like lowercase g for force due to gravity. You see that kind of both ways. And I'm cool with that. More generally, in a universal sense, there's this thing called Newton's universal law of gravitation where we talk about F big G. And so I'm going to distinguish myself between F little g being when we're close to Earth's surface and we're making use of the local gravitational field intensity, that local acceleration due to gravity near the Earth's surface, because of course it's going to drop off as you get far, far, far from the surface of the Earth, right? Like this little g is going to be true if I'm a person sitting on the surface of the Earth. But if I find myself like way out here in some sort of a space satellite or, I don't know, like a space station mission or something like that, I won't be experiencing the same acceleration due to gravity. I'll be far from Earth. And so we have to come up with a different model for that. And one of the models that we deal with is the universal law of gravitation, where it's F big G, which was determined from Cavendish's experiment, times the mass of the larger body times the mass of the smaller body, divided by the square of the distance between their centers of mass. And so that's something that where we would have to maybe go into that a little bit more in depth, and we could even talk to the general relativity people to see why maybe we have some different takes on this than we did back in Cavendish and Newton's day, and things are maybe a little bit different now. But for now, we're going to stick with this as being our model for how universal gravitation works. And then with electric fields, there's actually a similar formula that we're going to explore this year. I'll just call it FE, no big E or anything, but it has to do with something that's almost analogous to the big G, but for electric fields. We'll just call it an electric field constant, K, Q1, Q2, where Q1 and Q2 are actually the magnitudes of the charge. We measure that in coulombs, divided by R squared. And again, without going down this this rabbit hole in any kind of depth, we can see that there's a similar format. And if I said they're both inverse square laws, you'd be like, yes, yes, I can see that they're both inverse square laws. And we can talk more about the complexities of that later. We'll talk about electrostatic force, we'll talk about electric fields, we'll talk about electric potential and electric potential difference and how it relates to these sort of like overlapping ideas. And it'll be new and different than gravity, trust me, okay? But then we also talk about magnetic fields. And one formula that talks about magnetic fields, which we haven't talked about yet, might be QVB sine theta. And you're like, oh my gosh, well, whether you've seen that equation or not, it looks like there's some trig involved. If there's a sine theta involved and two vectors, then depending on your level of math, you're looking at that and saying, oh, is this a cross product? And I'd say, yes, it is a cross product. But if you haven't done that, it doesn't matter. This is something that we're going to explore, okay? So one way to talk about magnetic fields would be to calculate how fast a charge travels through a magnetic field and the force that that charge would experience. And we'll come back to this, okay? I mean, there are other things that we could talk about in terms of magnetic fields. But I'm going to move past this, but you know, it's interesting to see that there's motion involved, that there's charges involved, and I think like a lot of people expect magnetic fields to somehow be separate from electric fields, but you notice that we put it under the same umbrella, electromagnetism. Clearly, if there's a moving charge involved, there's going to be an interaction between electric field and magnetic fields. There's going to be some sort of crossover, okay? So we're not going to call them distinctly separate fields, but they're related. And I can't take a magnet and expect that it's going to pick up an electron. No, that's not what we're talking about. We're saying that somehow magnetic fields influence the force on a moving charge. I'm going to leave it at that and keep on moving, okay? Because these are fundamental forces and they deserve more time than this. This is just like the quick survey. Now, in terms of the strong nuclear force and the weak nuclear force, I'm just going to make a bold statement and say, for now, let the chemistry teacher worry about this. And we may or may not come to that, but for now, you're going to talk a little bit more about those strong and weak nuclear forces in chemistry class than you're going to talk about it in physics class. That doesn't mean that it's not physics domain. Chemistry and physics have like huge overlapping domains, obviously, right? Hey, we were just talking about electrons, and keep your eye on that one, wink, wink, right? There's going to be an overlap with that, possibly with chemistry. Get it? Ion, charge, anyway. So we're not saying that we won't come back to it. We won't say that it's exclusively chemistry's domain. And clearly, if we're talking about dealing with nuclear fusion and nuclear fission, then this is something that would have to come back in a physics course, right? But I think I'm going to leave that where it is. Bottom right-hand corner here, there's a little bit of thinking. And we've talked about a bunch of forces, and I'll leave that thinking with you, okay? I'm going to stop recording.